Hello everyone, this is Dilleswara Rao from Aeronautical department. So now today we are discussing about modeling of control systems part 2. Last few classes we are discussing on control system design and its operation and how we need to design that control system and what are the things we that has been involved in this control systems, and how this control systems integration and operational amplifiers operational amplifier installation, and how that input signal has been given to that, and with that input signal how that output signal is being converted to give the required output for control surfaces also. We are discussing actually this has been given in displacement autopilot system SAS and CA systems also. We actually given some introduction about this, but introduction means that is a total application only. But here, how that systems have been designed, what are the things involved on that systems, and how to represent that output system accurately, so that we will see now. So let's go into the topic. So last class we discussed on modeling of control systems only, but there we given mathematical representation of mechanical and electrical systems, and how that mathematical models have been converted into integrators, and how that integrator has been designed in a controlling unit also we have given. So there we discussed about linear time variant equations and the state space transfer functions also we have given. So now we will do some more continuation to that things only. Let's go into the topic. So now we are discussing on Laplace transform solution for LTI state equations. So here that's LTI means linear time variant equations. So actually here what is the main case is we are giving that when we are doing one equation, that equation may be in a differential form. So when the differential form equation is converted into integrated form, after that integration the output function will come. So like that, for a equation is having two or more variants, like variants involved on that one. Last video, if you see, there will be two functions involved on that, and in a states function. And the algorithm also we said that the linearization of that. I mean, first that differential equation will be linearized. That linearized equation will be again integrated, and we'll get the solution. So like that, here also another important thing will be like time variant functions. If time variant functions are involved in if time variant functions are involved in these things, so how that time variant functions will be how we can get that time variant functions can be solved with available things also we are going to discuss now. So suppose see this LTI state function, so that is a linear time variant function. So there it's actually maps the function time into the functions of complex variable s, which is within the terms of real and imaginary part. Generally, the equation will have a two solution while we are using the Laplace transform of an equation. It will have a two one imaginary function and one real functions also there. If you see previously that root locus plot, on that root locus plot, how we plotted that one, like the imaginary and real functions are there. If that function root locus is near to that imaginary or above that imaginary, and how that has been significant also we have given. So like that, if LNTL function is having a solution of real and imaginary parts, s equal to sigma plus j omega. So in this complex frequency domain, the function can be manipulated algebraically to into recognize the known transform and then map it back into that time domain. So the Laplace transform theory generally discussed given by that has been very clearly that has been given in previous things. So here it will be like a review of that Laplace transform motioning. First, in general, that analysis of a dynamic system will produce a simultaneous integral and differential equation. As I said, the functions will get it from that will be generally maybe higher order or linear ordinary differential equation. That differential equation will be further solved, and then we will get the solution. So these equations would be transformed immediately, so that the initial condition terms that appear in Laplace transform deformation, differentiation and integration terms represent in a single stored energy equation. So that is, if you remember this equation, P for n y and plus the summation of I equal to 0 to n ai p I y will be equal to that summation of I 0 to n BIP IU. So here that equation, we are taking that equation as a summation of all the constants that has been changed with respect to that values given here. So if that equation, the initial condition terms will in the differential form will be or transformed, and can make a difficult to general deformation function, differential function are somewhat tricky to solve that one. So for that, the required conditions on the dependent variables. Therefore, to avoid the transforming the general ODE equation, that equation one that has been given, it will have a non-zero initial condition, and that derivatives on the right hand side. The derivatives on the right hand side will be converted like that. If you have if you give that equation differential function into that normal function, so that will be one method. The second method will be like using that Laplace transform function for this differential equation, and that unexacted no that unexacted systems. The initial condition, if there is no initial condition in terms appear after transformation. So if the equations have been differentiated so that the derivations of that input appear at input initial condition terms must be cancelled out with the initial condition. So see, here you see, suppose a function is having that given with the Laplace transform function. So that is given with L of x of t, and another function us will be equal to L of u of t. Then that if you apply the Laplace transform for that above equation, that will be like what x of x and x 0 plus will be equal to a x of s plus b u of s. Like if the Laplace transform is been given to this one, so that will be having a two constants a and b that has been given here. So the x of s will be equal to if s is going to that side, so that will be like si minus a inverse will be equal into x of this x of 0 plus 1 will be going to that side will be b into u of s. It will be like here we are making the total equation. We are taking out that equation and multiplying divide with that, then the total solution will be like s will be general equation. If you form it into matrix form, so that identical matrix I we have given. So so that si minus a will be the will be in matrix form. So then that y of s will be equal to c into s of si minus a inverse will be into x0 plus b of s plus dus. Like suppose another function for this we are giving a solution that will be like y of s if it is if we consider, then that will be equated to this one. Then if you imply that inverse Laplace transform for the above equation, that inverse transform Laplace function will be like what, e power at will be equal to L inverse of Si minus A inverse. So here that 3 and 4 not well suited with machine computation, and hand computation involves a prohibitive amount of amount of values also. If laborious process will be involved on that, and lower order than lower order dynamic system. So therefore that LT solutions may mainly interest in complex number description of system properties. Like here you see, if we give that equation, like for a one one matrix we form, and that will be submitted with SI, then that adjoint matrix, and if you calculate that adjoint matrix and all, we will get a big solution. But that solution will gives you laborious process for solving that one. But for a lower order dynamic system, it will be very difficult to get the solution. So for that, what we need to do, we will consider, we will make that as a one quadratic equation, like a minus lambda. If you see that eigenvalue, that characteristic equation, we will get it by taking that a minus lambda things. So here lambda means what? This yes only. So in terms of yes, we will get a quadratic equation. If that equation is in cube form or second order form, like generally it is a 3 by 3 matrix. I mean, if it is 3 by 3 matrix, it will have a 3 variables. So if one variable is available, another two variables may be complex variable, generally we will get, because whatever the things, if it is exact solutions are there, then that imaginary axis will be totally avoided. Only that real axis, real values only will present. But most of them we will get imaginary values only. So if you consider that imaginary values, then we will have a chance to get that equation into a definite form. So now we will see that how that differential equation will be represented in a transform function. Like a transfer function, generally you see in the previous things also, how the transfer function is being utilized for I mean, how the transfer function is being utilized for making that equation solution also. Like here you see, I mean, the transfer function for general thing, how it will looks like. So one summation amplifier will be there. That summation amplifier will be connected to one transfer function that is in S, and that is will be connected to that control system, and will be given to the S input. And here one a feedback amplifier will be there, and their feedback also will be I mean, feedback also depend upon that there is a separate function like gate function, filter function, bending functions also we have installed for the CAS and SAS systems. If you see previous videos, you will have an idea, like where we are making that transfer functions into an integrator. I mean, like an integrator, that integrator is giving the output values, right? So like that, here also, how the transfer functions are building up, like we are following on sequence. On that sequence, one mechanical representation system is there. That system is being transferred into integral form and differential form, and that differential form is conforming into this transfer form, that transfer function only. If that transfer function, how it will looks like see here we are taking that derivation of transfer function, like considering poles and the zeros. So consider a system by nth order ordinary differential equation, and the transform with zero initial condition, solving algebraically for function y of s, then that y of s will be equal to bm s m plus bm minus 1 s m minus s for m minus 1 plus bm minus 2 s m minus 2. Like that, it will be goes on, and it will be equated to b1 s plus b0. Like a series is been going on, and the downward function, like the downward function, that denominator will be like what, Sn a n minus 1 Sn minus 1. Like you see, if n equal to 1 2 3, like suppose if it is the third order equation, then it will be like what, s cube plus a1s square plus a2s a2s plus c1, like that. One constant function may be there. But suppose if more complex function is there, or a higher order function is there, then here that yes order also will be changes. So that is why we are considering that as a s power n. Like that means here n will be vary from 1 to n. So the polynomial function y of s to u of s will be the transfer function of will give the transfer function that will have a SISO system. This SISO system means what? Single input, single output, like this one. Like this is a single input and this is a single output, where there will be one feedback system also will be there. So this is SI system. If we have obtained transfer function U of S, then using the partial fraction technique for above equation, the right hand side of above equation will be broken into two parts. That sum of transform corresponding to that unknown time functions, and hence the phi of t will be found to be as a sum of time functions. The transfer function from LTI state equation. Suppose previously we said that LTI linear time variant equation in the matrix expression can be having like that. So suppose if we consider MIMO system, MIMO means what? Multi input, multi output. So multi input, multi output. So suppose if that function we have considered, then it is having I mean, if it is having p by m matrix, then the function will be like what? G of s will be equal to c into si minus a inverse for b plus d. Suppose this b d s b d a c, these are all matrix only, but in terms of constants, like if a number of equations are there, that number of equations will be converted into matrix, and that matrix will be forming as an equation. So if that equation is there, that we will represent with gs. So suppose that gs is there, then that transfer function will be unchanged by a non-singular transformation of that state variable. Then that will be write it like a if multiply with L inverse to everything. So that will be like what? L inverse into C into Si minus L inverse into LB plus D. Then that if L inverse we are taking out as a common, then that will be like what? L inverse of Si minus L inverse AL L inverse into for inverse into B plus D. Then that is totally we can write it like a C of Si minus A inverse of B plus D. So here the matrix of Si minus A is already in inverse form. So the matrix inverse can be expressed as a adjoint matrix by det matrix. So generally what is A inverse, we will write it like adjoint A by det A, right? So if it is a 3 by 3 or 2 by 2 matrix, that adjoint matrix will be each characteristics value by the det of that matrix. So here that adjoint of Si minus A, that Si minus A will be the whole matrix, that adjoint of Si minus A into B plus D into Si minus A by I mean, if it is a det A, so only this will have it I mean this can be write it like S of adjoint of Si minus A by det Si minus A plus into B plus D. So if you write it common, then this will be going that side and will multiply, so that that Si minus A will be here by Si minus A. So the transfer function from jth input to the ith output is the ij elements of GIS, G of S, and the SAS for that single input, single output, single input and single output system. transfer function, we can write it like Gij of S. So this is a SISO type of transfer function. So that can be write it like that GCIS will be equal to CI. I mean ith term and jth term we are considering here. So CI adjoint of SI minus A BJ. I mean BJ element we have considered plus Dij of Si minus A by Si minus A. Like means here ith term and jth term of each matrix term we are considering here. Then total matrix will be like what? That Si adjoint of Si minus A into that coefficient of ith term and jth term. That coefficient ith term will be like Ci and the jth term will be Bj. And that ij term will be like what? I mean ith term jth term means what? Suppose if it is like that, AI I mean this will be Aij, and this is ith term only, Ai plus 1j and Ai plus 2j, like that it will go. And this will be like what? A I mean generally we will write it like this will be Aij. I mean this is ith row jth term. Ith row jth term will be like what? This is Aij. Ai plus 1 j plus 1 I plus 2 j plus 2, like that things will be go on. Like downward also will be like what? Ai I and Ai I comma j plus 1, I comma j plus 2, like that the ith column will be common and the jth term will be going forward. So suppose if you are considering that that terms we will be making it as a normal terms. So generally that ij terms will be making it as a matrix form. So that matrix form coefficients only we have considered here. Like what is given here, that the jth input, to the ith output of that ij terms and of the elements in GIS. That jth input and ith output we are together considering, and that values on it. I mean output also how we are giving here, that output is giving through that feedback formula. So like that, feedback form also we are fed into that one. So that will be like a ith input term will be there. That is Ci only. So the total function will be like what? Ci of adjoint of Si minus A of Bj plus Dij Si minus A by Si minus A. So where the Ci and Bj are respectively the ith row of C and jth column of B. Like I said, no, ith row and jth column of B. So the transfer function is a rational function of two polynomials. The elements of that adjoint matrix are by definition. The element of adjoint matrix will be by definition. We will write it like cofactors of Si minus A only, and are therefore polynomial in degrees of Ni minus 1 and lower. So the determinant of Si minus A will be the polynomial equation only, because generally we will we have a equation. If you consider that characteristic equation, how we will do general in matrix form, if you remember that A minus lambda I will be there. So on that this total things will be like lambda cube plus lambda square plus lambda plus 1, like that one equation will form. On that this is called it as a characteristic equation, and that characteristic equation will gives you the values for lambda. So same as if that Laplace transform operator, that S in terms of equation S cube S square, like that, then that equation will be considered, converted in like that, and that equation will be making it as we can write it like a quadratic equation, polynomial equation. That polynomial equation will have a different solutions also, like P1, P2, P3, Pn solutions are there. If nth order equation is there, then Pn solution will be there. Like if n equal to varies from 1 to n, like 1 to n variables are there, then 1 to n solutions also will be there. So that only we have given here, that is S of S plus P1, S plus P2 up to S plus Pn, and that S plus P1, and that numerator is like what, S of Z1 and Z2 and Z3, and these are all the functions, I mean coefficients of that each the matrix involved on this one. So that is like what, S K into K into S plus Z1, and K into S plus Z2, and up to S plus Z1. Zm, like we are making that into partial fractions. So the denominator fractions of Si minus A, and it's evident from the previous equation. All individual SIS4 transfer functions will have a same denominator routine, because same denominator means what? Because downward function will be same only, and given by roots of that nth or nth degree polynomial function by Si minus A only. The roots Pi are called as the poles of the transfer function, and values of S will be the transfer function becomes that infinite in magnitude. Like that roots Pi is called as, like Pi means what? This P1, P2, P3 that are called as a poles of the transformation, poles of the transfer function, and at these values of S, I mean at these values the transfer function becomes infinite in magnitude. Like the transfer function values will have a many values we will get it at that system. So the equation 10, I mean previous equation 10 is there, no? So is a partial fraction function. Like partial fraction function, how we will get that A by Si minus, if you remember that partial fraction, how we will do that, if one equation is there, that equation will be divided into partial fraction by making that common denominator, and multiplying that respective values in denominator. So like that, the numerator will be like a partial fraction expansion of that transfer function only. So, and the coefficient of that residue of that poles Pi minus Pi, that means Pi means what here, if it is an imaginary values, like complex variables are involved on that one, so that may be in terms of minus. But if real values are there, then values may be positive values also will get. So in these complex poles, the partial functions of the partial combine as a conjugate pairs. That poles of multiplying multiplicity k will require a numerator of degree k minus 1, and that can be further broken down into finite expressions in inverse powers, that is S plus Pi. So I mean if the poles of that multiply k will require a numerator of degree, like if that values are having degree of k minus 1, and that can be further divided into finite expansion value, that will be like S plus Pi. So the zeros of the individual SIS4 transfer functions are the positions of positions in the S plane, where the magnitude becomes 0 only, because when an SIS4 transfer function, the positions in S plane will be like, because they are all Pi values only, so in S function it will be zeros only, and that the roots will be minus Zi of that numerator polynomial, that is you see that Z1, Z2, Z3 is there, no, in equation 7, like a previous equation. So so the number of zeros of SIS4 transfer function will change from 0 to n. Like suppose if roots are in a real function, if roots are in a real axis, and if that zeros, I mean wherever the roots are there, the S plane will be having 0 values on it. That means if that imaginary axis values are 0, then S plane values will be zeros. Then if that zeros are zeros of that SIS4 transfer function will ranges from 0 to n, that will be depending upon the degree of the transfer function only, because
whenever that degree of transfer function is been increasing, like higher order functions like s power 4, s power 5, that type of functions are there, then the zeros also will be involving. The zeros means it's not like a zero value. There the s values are getting zeros only. Suppose if x and y values are there, only y values are involved, means what, that values will be on y axis only, no. When s values are not there, but that imaginary axis values are there, then that values will be present as an imaginary values only. That means the complex number of values. So the SASO input transfer function will be ranges from that 0 to n, like it will be going from 0 to n. And that if order of that transfer function also, if it is having changes from 0 to n, that values of zeros also will changes from 0 to n. So this is about this transfer function, how the transfer function will be designed for a control system. So here what we learn like what is a linear time variant function. If it is in a differential function, make it into matrix function. That matrix function will be matrix function will be solved with Laplace transform functions only. Laplace transform function, if you use for that, then it will be transferred into Laplace equation, Laplace operator. In terms of Laplace operator, that Laplace operator will be gives you the roots of that s. That roots of that s is call it as a poles. And if that if poles are only present, and if the s plane values are not present, then that is called it as a zeros. Okay, so that means here we are considering like the transfer function design of an thing, like you see here, this is the transfer function for a GIS. So this transfer function we have been taken from these values. Like this is what this we previously got it from that matrix form only. So here that matrix is involving what, that adjoint matrix and the adjoint matrix and coefficient matrix also be there. So if that coefficient matrix is solved, and we will get a bigger equation. And down denominator also we have a det matrix, so that is in already a big function. So if a polynomial function and a linear function is there, if you want to get the solution of that one, like if the equation is like that, and that solution of that equation will be taking out from partial fractions of that equation. So that partial fractions will be like what, like this partial fractions of above equation, we can write it like that. So here each value will have a yeah, roots for yes, and that numerator will gives you the coefficient of that equation. So like that we are performing the transfer function for an integrator. So in this how much you got it, maybe this may be some complicated things only, but you have to concentrate on how any system, whether it's a mathematical or whether it's a mechanical or maybe electrical system, how that has been transferred into normal differential function, how that differential function is being transfer making it to state space function. From that state space function, how this transfer function is being involved, so that you need to know. So once you know that one, like that you will design one transform what in the integrator circuit only. That integrator will gives you what are the desired input required for this operating this system. So this is all about this video part 2 of modeling of system. So next also there will be a continuation video is there with this thing also. In next class we will see it, the frequency response and time rate graphs, time response graphs and frequency response graphs, how we will draw it for this control systems also. We will see it in next class. So that's all about this one. So if you have any doubts on your side, you can refer this book, Stevens PL. So you will have a further clarification. So that's all about this.
Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.